In this session, I'm going to implement principal component analysis on our dataset. So I have taken a Minimis dataset where we have around 785 columns from 0 till 784. So let's see how we are going to build a feature selection model using PCA. Okay. Let me import the libraries first. So import NumPy as NP, pandas as PD, matplotlib pipe dot as plt, import c1 as essence. I'm also importing principal component analysis. The module named sklearn.decomposition from sklearn.decomposition. We import principal component analysis. Okay, we run this code. Okay, it's fine. And also, let's say we want to for that. So now let's import data. So I will call data frame. So pd dot read underscore csv of I'm going to import this MNIST data set. So let me say df dot head. So the you can see that so many of the features of the independent variables are not visible over here. So for that, I'm going to do some operation. So in pandas, we can set pd dot set option. We have pd dot set option. So here we can set the number of maximum rows or columns we want. So let's pass max rows I want as 500 and also pd dot set option max columns I want is so this should be max underscore columns and this should be max underscore. Okay, max columns I want are 500. So run this code. Now you run this, okay? So you can easily see now that we have around 500 columns that are visible over here. So we have our data set from 0 till 784th column. So now let's prepare x and y. So prepare x and y. X is equal to df dot. So before x, I will take y. So y is equal to df dot iloc of all the rows I want and only is the 0th column. Okay. Now, and also you could see that the 0th column is 0. So instead, we can directly pass 0 as well, but let me pass 0 here. Check what we get. Data frame object has no attribute dot iloc. Okay. So if you want to pass 0th column, you can easily go and pass here in a form of string. Okay. Now let's take y. X now x we will take. So df dot drop of we don't want 0th column. Okay. So we will drop 0 and axis we have to pass as 1 because we are considering column, right? So this should be mentioned in the form of list. Okay. So we have our X and Y. So let's see the shape of the data frame. So let's see the shape of our data frame. Okay, df dot shape. So you could see that we have 3047 rows and 785 columns. Okay. So now the data set has 784 columns as explanatory variables. So this one I'm discussing. And one y variable named 0, which tells what digit the row represents. This tells what digit the row represents. We won't use the y when creating principal components. Okay, you need to remember that we don't use y when creating principal components because I don't want PCA algorithm to know which class a particular row belongs to. Okay, so we don't want our PCA algorithm to know which class or digit a particular row belongs to. So rather, I create principal components using only X. So I'm going to take only X and build principal components. Later, we will see we will draw scatter plot using the first two principal components and color the points based on the actual Y. Typically, the X's were informative enough. You should see clear cluster of points belong to the same category. So now what I'm going to do, I'm going to do principal component analysis. Let's instantiate principal component analysis. So I have instantiated principal component analysis. So df underscore PCA is equal to principal component analysis dot fit transform I will perform. So fit transform on Rx variable. Okay. So now this, so we have our array created. So now store it in the form of data frame. So data frame PC principal component analysis is equal to PD dot data frame of, you have to pass df underscore principal component analysis. Okay, now let's print the shape of PCA. Okay, so okay, we got the shape. So we have 3047 rows and 74 columns. That is our X. Okay. Now let's see df underscore PCA. So you could see that there are so many like number of digits over there after the decimal. So let's round it off to two decimals. So df underscore PCA dot round off till two decimal dot I want to view head. So this is not rolling. This is round off till two decimal and we want head. Okay. Okay. So we have our standardized data. So the data has been standardized and we have got our principal components. So this is PC1, this is PC2, this is PC3, and so on. Okay. So let me explain it theoretically. The first column is first PC. Okay. This is first PC and second column is second PC and so on. The data frame df underscore PCA has the same dimension as the original data frame data X. Okay. This is X I'm saying. So percentage of variance explained with each principal component. Okay, we'll see that. The PCs are usually arranged in descending order. So, okay, this is PC1, PC2, and so on. Okay, so the PCs are arranged in descending order of the variance explained. Okay, to see how much of the total information is contributed by each of the principal component, we will use explained variance ratio attribute. Okay, so let's print the explained. So df underscore PCA dot explained underscore variance underscore ratio. Let me take this, and we will want the explained variance ratio only for the first 10 columns. Okay, so we want only for the first 10 principal component. Data from object has no attribute explained variance ratio. So we have taken PCA, right? PCA, PCA. Okay, so we had to take PCA, okay? PCA is what we want. So let me rewrite this code. So print PCA. So this is our model, right? PCA dot fit transform. So we'll take PCA dot explained variance ratio, okay? And we'll take only the first 10 columns. So you could see that here we have got decimal point till 5. So we have got decimal till 5. So we round it off, dot round off till 2. Okay, so now we have got the percentage of principal component analysis, that is PC. PC, the percentage of principal component explained by each PC. Okay, so we have 22% explained by PC1, we have 10% explained by PC2, we have 6% explained by PC3, and 6 by PC4. So this can be more, but always understand that PC1 is always greater than PC2, always greater than PC3, for variability explanation. Okay, so we can do a plotting for this. Let's plot on. So what I would say is that, so the pieces are usually arranged in ascending or descending order of the variance information explained. We have already seen that. To see how much, so this is PC1, PC2, PC3. To see how much of the total information is contributed by each PC, we have used explained variance ratio. How to read this? So PC1 contributes to 22%, PC2 contributes to 10%, and PC3 contributes to 6%, and so on. Okay. The further you go, the lesser is the contribution of the total variance. You could see that, right? So initially is the highest, and the last is, as you go, it will become decreasing. Okay. So now we do plotting of cumulative sum. Okay, so we will add these values 22, 10, 6, 6, 4, 4, and we'll do cumulative sum for the, like let's say for all the explained variance ratio. Okay, so let me print plot plt dot. So before that, so we are going to take variance explanation cumulative sum, the variance variable variance explanation cumulative sum. So this variance explanation cumulative sum will add up each of the principal component analysis values and see at what number of PCs we will get the highest variability. Okay. So how many features? I mean, it will tell us how many features if you consider you will get maximum variability. Okay. So since there are 74 rows, 74 columns, we don't want all 74, 84, 748, 784 features to be used, right? So we will try to see at what value of number of features, I mean, how many features we need to get maximum variability as possible. So it can be calculated by variable explains cumulative sum. This is equal to PCA dot. Okay, so we'll take explained variance ratio dot cumulative sum. Dot cumulative sum will calculate, and we will round it off to till 2 decimal. Okay. So now, so let's figure my axis is equal to figure of fixed size. So we are taking subplots right here, figure comma axis we have passed. So PLT dot subplots, or we can just go with figure. So figure of pig size equal to 10 comma 8. Let's consider. Okay. Now we'll do the plot PLT dot plot of variance x plus. So I'll take fixed size as 16 comma 7 instead, so that we'll get maximum explanation. So now we'll do PLT dot plot for variance explained cumulative sum. So variance explained cumulative sum. So and let's give color as, let me pass orange instead. So let's see how the plot comes before moving. So figure is not defined. PLT dot figure of pixels. Okay, so we have some error. O is not a valid orange. So we'll give fire brick. Okay, so we have got the plot. So let's define x plt dot x label as, so principal component, that is number of principal component. Number of principal components is nothing but number of features we are considering. And plt dot y label is the variability, the variance or explanation. Percent variance explanation, let me consider. Percent variance explanation. So let me run the code again. So let me increase the size. So font size, let me increase it to 16. Both X and Y, horizontal and vertical, I have increased by size. So you can see percent variance explanation is Y variable, Y column, and percent of principal components. These are independent one. Okay, this is the dependent and this is our independent one. So now let's plot, we give a title as well, plt dot title of a screen plot of variance explanation percent. Screen plot variance explanation percent. Font size will pass as 22. Okay. So we have our plot for the variance. So you could see that at number of principal components 100, if you consider out of 780, if you consider it 100, we are getting almost 95% of the variability explanation, variance explanation. And at 200, if you take, it's almost equal to 97%. And at 300, it's almost equal to 99% of the variance explanation. Okay. So you will get 100% of the variance explanation at around 350 value. Okay. So number of principal components, you would take 350, you would get almost 350, almost 100% of the variance explanation. But you can go with any value, like you can go with say like 50. At 50, you are getting around this value, right? 50. At 50, you are getting almost 90% of the variance explanation. So you can go with 50 as well, or even 100. So depends on how many features you want. Okay, so try to have a less number of features and which is having highest number of variance explanation. Okay, so next. step is how to get our original features back. So this is our principal component features, right? So let's get back the original features. Okay. The fitted PCA object has inverse transform. Okay. Method that gives back the original data when you input principal component features. So let's get back the previous data. So DF original, let's say original data frame that we can get by PCA dot inverse transform of DF underscore PCA. So now let's create PD dot data frame of DF underscore origin original data frame. Okay. So when you print this, you'll get. So let me round it off and consider only head. So we have to take. So let me run the code now. Okay. So let me pass the cheap. So we have got all the values back. Okay. So this is our original X that we have considered. This is our original X. So we have got back our X using in fitted PCA in principal component. We have used inverse transform to get our original data frame back. So this was all about principal component analysis. I hope you understood everything I thought. So this is how we are going to choose the value of principal components for which explains the maximum variance as much as possible, and you can break down the number of features that you want for building a model, and you can build a model. You can go and build a model now because we have reduced the number of features based on the number of columns you want. Like you can go with the value you want now, since we have plotted the graph, and almost at 100 it explains almost 95%, 93 and 94% of the data, like 94% of the data is being explained. So this was all about principal component analysis. Thank you for attending the session. Hope you enjoyed the session, and I will see you in the next class for support vector machine.